Chapter 10, we are going to look at it in a condensed manner. Here are the 6 sections we will look at. In this first video, we will look at sample space and probability. If you've been watching the news, they've talked a lot about probability lately. We want to understand the possible outcomes in a sample space experiment. So what is a sample space and what is an experiment? And related to that is, how many of you have ever thought of the odds of winning a game? This is based on the probability of an event occurring within a sample space. So hopefully you are playing some games now that you're sitting at home and enjoying time with your family. So let's first figure out what is the sample space of an experiment. So if I have 3 coins and I flip them, I'm going to list the possible outcomes, and order doesn't matter here. So I could have a heads and 2 tails, or I could have heads, 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 or tails, tails, tails. And here are my possible outcomes when I go to list all of those. This last one, it should be a T. I don't know why we can't quite see that one. But I could have 3 heads, I could have heads, heads, tails. A quick way of figuring this out is I have 2 outcomes, a head or a tail, and I have 3 objects. Outcomes raised to the power of the objects. That gives me 8 possibilities. So rather than listing them all out, remembering this little formula is helpful. So to figure out the possible outcomes, that would be your sample space of an experiment, you start out with how many outcomes raised to the power of the number of objects. So if I have 2 fair number cubes, we call them fair number cubes because a dice or a die could be weighted and then it would not be fair. It would always come up with the same number. So I roll 2 die or 2 fair number cubes. I list the possible outcomes in the sample space. So I could get a 1 and a 1, which we call snake eyes, a 1 and a 2, 1 and a 3, 1 and a 4, 1 and a 5, 1 and a 6. Or I could have a 2 and a 1, a 2 and a 2. I can go all the way up to 6 and 6, and that's called box cars, kind of like a railroad box car. I have 2 objects, my fair number cube number 1, my fair number cube number 2. I have 6 outcomes, so number of outcomes raised to the power of number of objects gives me 36 possible outcomes in this sample space. So we have theoretical probabilities, and that would be based on theory, not based on environmental things or conditions that might affect. This is based on theory. So the probability of an event is either going to be 0% of it happening or 100% of it happening, or maybe somewhere in between. Is it going to rain or not? Well, our weather director over there on channel 40 will say, oh, we have a 70% chance of rain. So right in here, it's likely it will rain. So probability can be expressed as a decimal, 0, 0.25, 0.5, 0.75, or 1, or as a percentage, 0 to 100%. 100%, it will definitely happen. So our theoretical probability is calculated the number of favorable outcomes over the total number of outcomes. The total number of outcomes would be your sample space that we just looked at. So our favorable outcomes over our total number of outcomes. The probability of an event, that is the likelihood or the chance that it will occur. So remember, it's measured from 0 to 1, and it can be a decimal, or a fraction, or a percent. So the probability it's going to rain today is 30%. Now we have the complement of that event. That would be that it is not going to occur. The probability it is not going to rain is 70%. These two will add up to 100%. So here's a little formula. The probability of the complement of the event is 1 minus the probability of the event occurring. So the probability of an event, of the complement of the event, is 1 minus the probability of the event itself. Or I could add the complement and the event together, and it'll equal 1, or 100%. So let's flip a coin and roll a 6-sided fair number cube or die. So what is the probability I'm going to get a heads and a 6? And we're going to write it in all three forms. So first I need to know what am I looking for? Well, the probability of rolling a heads is 1 out of 2. I have 2 chances in my sample space, a heads or a tail. So I have a 1 out of 2 chance of rolling a heads, which would also be 0.5. The probability of rolling a 6 is 1 out of 6 chance, because I could roll a 1, 2, 3, 4, 5, or 6. So I have a 1 out of 6 chance. Well, what is the probability that I do both? See the and, that I do both. So the probability that I will flip a heads and roll a 6, I'm going to take those two percentages and multiply them together. I'm going to have 1/2 times 1/6. That's going to give me 1/12. I can convert that to a decimal, which is 0.08, and I can change that to a percent. So I have it in fraction form, percent form, and decimal form, all three forms. But notice when it said and, I multiply. So let's find the probability that the sum is not 6. When I roll two dies, the sum is not 6, or the sum is less than or equal to 9. Well, we can approach this a couple ways. When I look at where's the sum of not 6, it's really easier to look at where is the sum equal to 6. So I can get a 6 with a 2 and a 4, a 3 and a 3, a 4 and a 2. There are 5 possibilities there of rolling a sum that is equal to 6. So 1 minus 5 over 6 is 31 over 6. It was a lot easier looking at the complement. How many times do I roll exactly a 6 and subtract that from 1? Now, where is the sum less than or equal to 9? Well, there's a lot of places where it's greater than 9. So where is it less than or equal to 9? Well, I can go through and I can look at the complement. There are 6 places where my sum is less than, where it's greater than or equal to 9. So most of them down here, it's where it's going to be greater than or equal to 9, kind of in this lower L-shaped area. So there's 6 out of 36 where it will be greater than or equal to 9. I use the complement theorem, and so I have 30 out of 36 times where it is going to be greater than or equal to 9. I then take a closer look at that. Where is it going to be less than or equal to 9? And that is 0.833 or 83%. So now if I am throwing a dart at a dartboard, where am I most likely to hit a point inside of the square? All right, so where am I most likely to get 10 points or 5 points or 2 points or 0 points, right? So that's asking me to, where am I most likely to hit any point inside of the square? Well, here we need to look at the area of the circles. So the probability of getting 10 points, that's going to be the area of that smallest circle over the area of the entire board. Well, area of a circle is pi times radius squared. So pi times 3 squared is 9 pi. What is the area of the entire board? Well, this entire board, I have 3 plus 3 plus 3. So I am going to have 9 on this side and 9 on this side. So it's going to be 18 by 18. So 18 squared is the area of the entire board. So now I've calculated that. What is the probability of getting 0 points? Well, that's that little area out here. So I'm just looking at that little area out here. Now, I'm not going to quiz you or test you on a question like this, but I do want you to take a look at that. So experimental probability is based on repeated trials of a probability experiment. The number of trials is the number of times the probability of an experiment is performed. Each trial in which a favorable outcome occurs is called a success. So experimental probability is your number of successes over your number of trials. Here, if I have a spinner and I spin it 20 times in my experiment, you can see what the results are. So that shows, and they are all even areas. So in theory, theoretic probability, I'd have a 25% chance of reaching each color. But here I actually ran an experiment. So it's asking me which color is the experimental probability of stopping on the color the same as theoretical. Well, I just kind of said that, right? But here we've run it 20 times. So when I look at the probability of red, 5 out of 20 times is 1/4. And right here it is red is 1/4 of that circle. All right, I have to go to a meeting, so I actually have to pause this. All right, sorry about that. My meeting's over. So it says work with a partner. But if you have an experiment and you have a bag that has 2 blue marbles and 5 red marbles, and you pull 2 of the marbles out of the bag, it's going to make a difference if you replace them or not. So we always need to look closely. Does it say that we replace the first marble? No. So how many ways can you choose 2 marbles? How many ways can you choose a red and then a blue marble? How many ways can you choose a blue and then a red marble? And how many ways can you choose 2 red marbles? So we usually start out with listing the sample space, and then we want to figure out what are the total number of outcomes. So on problem A, how many ways can you choose 2 blue marbles? Well, there's really only 2 ways to pull 2 blue marbles out. How many ways can you choose a red and then a blue? There are 10 ways that you can do that, and we'll look down here in a moment. How many ways can you choose a blue followed by a red? And we will look down here at the sample space to verify that that is 10. And finally, how many ways can you choose 2 red marbles? And we would look down here. Okay, so in this sample space, we can pull blue 1 followed by blue 2, or blue 2 followed by blue 1. That would be your answer to this first one. How many ways do you choose 2 blue ones? Now, this is sort of a pain to actually write out because you really have to think that through. But look closely at this, because the test last year, I don't know what the test this year is going to be, but the test last year had a question like this. So by listing out the sample space, we can answer part A. Now, what are the total different number of outcomes that are possible? If you add all of these up, there are 42 different possible outcomes. So that is it for 10.1. That's a longer section because it does give a pretty big introduction.